Colligative properties are properties where when we dissolve things into a solution, it changes its properties. And these are very specific properties. So colligative properties are things that are dependent on only the amount of solute present, meaning that these things are the same for whether you've got sugar water, salt water, something else dissolved in the water. It doesn't matter. As long as it's the same amount, then that's all that matters. Okay, it is fully independent of what thing you put in it. And so that's important to know. So it's also important to know that when you're dealing with ionic compounds like salt, when you dissolve salt in water, the ions do what we call dissociating. So the sodium and the chloride, they don't stay together when you put them in the water. They actually split apart. And therefore you end up having twice as much dissolved in there than you would have if you put sugar in there. So a mole of salt will have 2 moles of ions in it, where a mole of sugar would just have 1 mole of things dissolved in it, and that's important to know. We're not going to do any calculations with these, but that's just what you need to know. When you get into, if you were doing like a college chemistry course, then you would actually do calculations with these, or an AP Chem course. So first one is what we call vapor pressure reduction. So most common liquids will evaporate at room temperature. If you remember, when we talked about kinetic molecular theory, we said that temperature is the average kinetic energy, and that to think of it kind of like a bell curve. So here's my room temperature, and I've got a bell curve. Some of these guys down here are going to have enough energy to evaporate. Think about it. If you have a water bottle, you drink a little bit out of it, and you put the top back on it, and you leave it on your desk for a couple hours, when you come back, there's going to be water droplets on the top, like on the inside. Okay, that's some of the water in the bottle having evaporated and then recondensed on the inside of the container. That's common. Okay, so evaporation occurs. Now, when the vapor is formed by evaporation, it exerts a pressure on the surface. Because once again, these molecules of water that are floating around up here in their vapor form have mass. And because they have mass, they exert a pressure down on the surface. This is called vapor pressure. Okay? When you dissolve something in it, it's going to get in the way here, make it harder for things to evaporate. So it prevents them from evaporating easily, which means you have less vapor, which means you have less vapor pressure. Okay, so this is the first colligative property. When I dissolve things in a solution, they're going to produce less vapor, which means they're going to decrease their vapor pressure. Right, this is on a practical scale, not one of those things you're going to run into a whole lot. However, it is the foundation of the other two, or the next two. And so that's why we need to learn about vapor pressure reduction to start with. So everything produces a vapor, most liquids do. If you dissolve something in it, it's going to decrease the amount of vapor that forms, decreasing this vapor pressure. All right, so boiling point elevation. As the name implies, when you dissolve something in water, its boiling point will go up. So we need to define what boiling point means. Boiling point is defined as the place where the vapor pressure and the atmospheric pressure are equal. What's going on here is as the vapor is heated, so you're heating your water in a pot. You'll notice as it's heating, so you start off with room temperature water, and then as you heat it, you start making more vapor. So when it gets up to 50 degrees C, you got a little more vapor, so you got a little more vapor pressure. Then you heat it up to 75 degrees and you're starting to get a little more what looks like steam above it. You're getting a little more vapor pressure and you got a little bit more going on. Now it's relatively slow at first. So we went from 3.2, 12.3, 38.5. We're still way down here. We're still a long way away from 101 kilopascals. But as we approach boiling point, the amount of vapor begins to increase dramatically. And then once we reach the same temp pressure, then we have boiling. So this is part of the why when you put a lid on a pot, it will boil faster because you're trapping that vapor. And by trapping the vapor, you're going to increase the vapor pressure faster. And so that's the basics of boiling, or what boiling is. And so boiling is simply we're increasing the amount of vapor above the water. We exert a pressure on it. And when that vapor pressure pushing down on it is equal to the atmospheric pressure, we will boil. All right. This is also significant in terms of elevation. Because if you decrease the atmospheric pressure, let's say you go to Denver, and you go there, atmospheric pressure is going to be lower. And therefore, you're going to need less vapor pressure to equal it. And therefore, water will boil at a lower temperature. Like I grew up in Atlanta, and in Atlanta, water doesn't boil at 100 degrees Celsius. It boils closer to 98. We're at about 1,000 feet elevation in Atlanta. But it made enough of a difference that we had to calibrate our thermometers differently when I was in Atlanta than we would if we were at sea level. And so this comes into play there. Now, back to colligative properties. So what's going on here is that the solute molecules cause a decrease in the vapor pressure. We've already talked about that, vapor pressure reduction. Because of that, we have a lower vapor pressure. So pure water at 100 degrees Celsius, we're going to be at atmospheric pressure, we're going to be boiling. But if I have seawater, ocean water, the vapor pressure is still not there yet. I'm still not to 101. And so this will not be boiling yet. I'm going to have to heat this up to 104 or 105, something like that, before this vapor pressure gets high enough to actually boil. And so because of that, I've got to increase the temperature to make it boil. It elevates that boiling point. Right. Now, when you add salt to your water when you're cooking potatoes or pasta, you're not adding enough to actually increase the boiling point by any measurable amount. It's primarily for flavoring. It doesn't make it cook faster. It doesn't really have an effect here because you're not adding enough. You have to add a whole lot of salt in order to make this effect noticeable. Because look, we're only looking at, what, 1.5 kilopascals difference between these two? Between pure water and ocean water. And ocean water is really, really salty. And so you have to add a whole lot of salt to get a little bit of effect here. But you will have to heat this higher, beyond 100 degrees, in order to boil it for that reason. All right, freezing point depression. The actual mechanics here that's going on is kind of complex. So the easiest way to think about it is that basically the solute molecules just get in the way and keep the crystals from forming. That's really the easiest way to think about it. It is related to vapor pressure in reality. And so vapor pressure affects it, but it's complicated. So the way I usually explain it is just simply saying, hey, if you're trying to, you got some Kool-Aid that you're trying to freeze, all those Kool-Aid molecules are going to get in the way of the water molecules freezing and makes it harder. This is why we add salt to roads. So you add salt to the roads and it causes the freezing point of the water to drop, therefore hopefully becoming water again instead of ice. This also, if you've ever made homemade ice cream using like ice, you add salt to the ice. And what that does is it drops the freezing point of that salt water mixture and ice mixture and allows it to get below 0 degrees Celsius. You can get it down to -4, -5 degrees Celsius by adding the salt to it, which allows it to be cold enough to freeze the cream and everything that you're making the ice cream from. Increasing the amount of solute will increase the amount at which you depress the freezing point. Up to a point. There comes a point when you're adding salt to your ice cream mixture, the ice solution on the outside, that the salt's not going to dissolve anymore. You can't make it go any lower. But adding more salt generally will help that go faster. All right, so that's the first three. Vapor pressure reduction, boiling point elevation, freezing point depression. Osmotic pressure. So you've probably heard of osmosis, the process of water moving across a membrane. And so we talk about this when we're talking about a semi-permeable membrane, something like a cell wall. That's not perfectly permeable. Usually water can move across, but the solute cannot. Okay? And so that's what we're talking about. And nature likes balance. So if I've got a high concentration on one side and a low concentration on the other, nature's going to try to equalize this. It doesn't like this. And so if I've got high concentration on this side, low on this side, and I got a semi-permeable membrane in the middle, that I can't take the salt from this side and move it over. All I can do is move water. The water is going to move this way. Why? The water is moving in an attempt to dilute this side. Okay, so it's trying to dilute that highly concentrated side and trying to make them be equal. All right, so this comes into play in multiple places. So the moving water exerts pressure, and the more water you have, the more pressure it exerts. So this is a really, really important process in biology. Plant rigidity is this way. Think about wilted vegetables. Like if you got wilted carrots or wilted celery, you stick them in some water, they will perk right back up again. And so what's happening is if you have low concentration and higher concentration of salts inside the cells of the celery or the carrot, and you put it in water, the water's going to flow in trying to dilute this. You have more water in these cells, it makes them more rigid, and you get a firmer thing there. Now, if you take a freshwater fish and you try to put it in salt water, it will die. Part of the reason being, once again, osmotic pressure, osmotic flow. That for that fish, relative to the salt water outside, its body cells have lower concentration. And there flows the water out, trying to dilute this out here. Same thing with your lips when you eat salty chips. Your lips will kind of shrivel because the water leaves, trying to dilute that salt and make the sides be equal concentration. And so that's osmotic pressure. So your four colligative properties, and once again, they are not, it doesn't matter if it's salt water or sugar water. You could put a fish in sugar water and it would still have the same problems. So when you're dealing with these colligative properties, it's all about how much you have in there, not what you have in there. And then it's all about its vapor pressure reduction. So vapor pressure goes down, boiling point elevation, boiling point goes up, freezing point depression, it goes down, and then osmotic pressure. Water flows from low concentration to high concentration, trying to equalize everything out.